Everybody, in this video, I'm going to go through our lesson on trigonometric ratios. So let's first start talking about what the different parts of the right triangle are. So in right triangle ABC, and I'm going to put my picture, I have a preloaded ABC here, right triangle. We're going to let angle A be called theta, and this is a Greek letter pronounced, oops, I knew I was going to misspell it, theta. So angle A, this is going to be theta. We're going to talk about the different side lengths in relation to this angle A. So as I look at this right triangle, and actually let me kind of shimmy this over a little bit. Oops. In the right triangle, the side opposite the right angle is always the hypotenuse. So I know our hypotenuse is this side AC. If I am talking about in relation to angle A or theta, the side that is opposite angle A or opposite theta is BC. So this is our opposite side. So I would say side BC is opposite angle A. And then that leaves us with the leg that is directly adjacent to angle A. It's not opposite, it's not the leg opposite A, it is the leg that is adjacent to angle A. So I would say here that side AB is adjacent to angle A because it shares a side. Angle A literally touches side AB, and it's not the hypotenuse, it's the leg. All right, so we're going to talk now about what the trigonometric ratios actually are. There are three different ratios we're going to look at. I'll do this. Trigonometric ratios. And what these ratios do is they relate the side lengths of the triangle, of the right triangle specifically, to either of the acute angles. Acute angle. It has to be an acute angle. If you're using the right angle, these ratios are not true. So acute angle. Angle A or angle C in the diagram I just drew. The first trigonometric ratio we're going to work with, I'll do this in blue, is sine. Sine of whatever your theta is, that angle that you are interested in. So sine, abbreviated SIN, like a sin, sine of theta is equal to your opposite side over your hypotenuse. So here is that triangle. Get a little bit smaller. So if I am letting A be theta, the sine of A is equal to the opposite side, which is BC, over the hypotenuse, which is AC. So I would say that the sine of A is really like the opposite BC over AC, whatever those values may be. All right, let's talk now about cosine of theta. And either acute angle could be theta. So I could find the sine of C. That would be like the opposite AB over the hypotenuse still, which is AC. So the cosine of theta, abbreviated COS, of that angle theta, it is always the adjacent side, adjacent, over the hypotenuse. So here's that triangle again. Let's shrink it down. I'm going to keep A as our theta here, the angle that we're interested in or talking about. So cosine of this angle A is the adjacent. Let's see, adjacent would be AB over the hypotenuse. And the hypotenuse is AC. So both sine and cosine relate either the opposite or the adjacent to the hypotenuse. The one that is a little bit different is tangent. So the next one we're going to talk about is the tangent of theta. And this is often abbreviated as tan. So this is tan of theta, and that is your opposite over the adjacent. So the tangent actually does not involve the hypotenuse. It is strictly the opposite over the adjacent based on that angle theta. So here is ABC. A, I'm going to keep as theta. In fact, I'm going to scooch this up a little bit. So opposite would be that side BC, and adjacent is the side AB. So the tangent of angle A is equal to the opposite over the adjacent, which is really BC over AB. So how do you remember all this? How do you remember that sine is opposite over hypotenuse? Cosine is adjacent over hypotenuse. Tangent is opposite over adjacent. We have an acronym. So, no. So what this represents, I'm going to take it piece by piece, starting with the first three letters. SOHS tells me that the sine is the opposite over the hypotenuse. So S means sine is opposite O over hypotenuse H. The CAH, the ka part, means that cosine is the adjacent, oops, let me do capital A, over the hypotenuse. A for adjacent, H for hypotenuse. And lastly, TOA tells us that the tangent is equal to the opposite over the adjacent. So this is a very, very, very helpful acronym that I would write down in my notes, and anytime I'm doing some sort of trig problem, I would put this up at the top of my paper so that way I can refer back to it. So let's look at some examples. So we're going to start with a right triangle that looks like this. This is X, this is Y, and this is Z. And of course, angle Y is the right angle. The hypotenuse is 25. The shorter leg is 7, and the longer leg is 24. So we're going to answer a couple different questions with this. First, part A, we're going to find tangent of Z. And I'm gonna write my Z with a little mark through it so it doesn't look like a 2. Now, even though it's right above, the acronym is SOHCAHTOA. So if I want to find the tangent of Z is going to be equal to the opposite over the adjacent. Looking at the TOA piece for tangent. So let's look at Z. Where is Z here? So here's angle Z. So my opposite side, that would be XY, which is really 7, over the adjacent, which is 24, or YZ. So tangent is opposite over adjacent of this angle Z, which in this case is 7, the opposite side, over 24, the adjacent side. So I could write my answer in a couple different ways. I could say that tangent of Z is equal to 7 over 24. Or I could say that tangent of Z is equal to 7 over 24 as a decimal, 0.2916, and that 6 repeats. So either way works, but the ratio of the opposite over the adjacent for angle Z is 7 over 24. All right, part B for this problem, we're going to find cosine of x. So cosine of x, thinking about the acronym up here, cosine is adjacent over hypotenuse. So adjacent over hypotenuse for that angle x. So if I look at angle x here, the adjacent side right next to it would be 7. Right? That adjacent right next to it, not the hypotenuse. The hypotenuse itself is 25. So 7 over 25 is the value of cosine of x, or I could say that cosine of x is equal to 7 divided by 25 is 0.28. All right, part C. What is sine of x? So we did tangent of z, we did cosine of x. Let's look at sine of x. So sine of x, thinking about SOHCAHTOA up here, that would be opposite over hypotenuse. So sine of x is opposite over hypotenuse. And we actually were just working with cosine of x, right? That was adjacent over hypotenuse. I know the hypotenuse is 25. Purple, actually. I know the hypotenuse is 25. This time I need the opposite side from x. So the side opposite here is 24. So sine of x is equal to 24 over 25, which if I put that into my calculator, sine of x then is equal to, well, that divided gives me 0.96. So again, you could write your answer either way. I could write this as sine of x equals 24 over 25. Just make sure your fraction, of course, is simplified. It's always important. Let's look at another set of triangles. So number 2 actually has an image. And if you can't print this out, this is an easy one to just draw in your notes real quick. And for this, it's important to note that triangle KLM is similar to triangle QRP. We're going to start by finding the tangent of M, angle M. So that is in the smaller, barely smaller triangle KLM. So here is that angle M. If I'm going to find the tangent, I'm going to write out so tangent is opposite. Tangent of M is going to be the opposite over the adjacent. So the opposite side here from angle M, that is 16, over the adjacent side, which is 30. And note that's really like KL over KM. Opposite over the adjacent. All right, now that fraction I know will simplify. So if I write it out, tangent of M is equal to 16 over 30. Both the numerator and denominator are divisible by 2. So I'm going to divide both by 2 to reduce this down. 16 divided by 2 is 8, and 30 divided by 2 is 15. So the tangent of M is 8 over 15. Now, I'm not going to worry about the decimal version for this. For part B, what is the tangent of P? So I actually don't know much about triangle QRP, except for it is similar to KLM. So since triangle KLM is similar to triangle QRP, I know those side lengths are proportional. So if we're talking about tangent, let's just compare like the opposite over adjacent. This means the ratio of KL over KM, the opposite over the adjacent, in one triangle is the same ratio as the opposite over the adjacent in the other. QR over QP. Since they're similar, by the definition of similarity, all the corresponding parts are proportional. So I can make this claim that the opposite over the adjacent is equal, since M and P are both corresponding angles as well. So where can I go with this? Well, I know that KL over KM, we just found that. That is the tangent of M, right? So the tangent of M is actually equal to the tangent of P. Because the tangent of P, if I think about it kind of over here, tangent of P is the opposite side, which is QR, over the adjacent, which is QP. So the tangent of M, which we already know is 8 over 15, is equal to the tangent of P. So the tangent of P is 8 over 15 as well. So if you know two triangles are similar, then their trigonometric ratios are going to be the same as well. If you're looking at the same angles, right? I'm looking at angle M, the tangent of M is equal to the tangent of P. The sine of M is equal to the sine of P. Number 3. We're going to draw the triangle for this one. It's going to be a right triangle that kind of looks like that. And this is triangle OPN or NOP. And we know OP is 51 and NP is 12. So first problem we're going to solve for this, we're going to find cosine of P. And I can't see my SOHCAHTOA anymore, so I'm going to write it out. SOHCAHTOA. So I'm going to find cosine, meaning I'm interested in finding my adjacent over the hypotenuse. So if I locate angle P, the adjacent side, not the hypotenuse, but the side touching it, that's not the hypotenuse, the leg, that is OP. So this is really just OP over the hypotenuse, which is NP. So really, this is the square root of 51 divided by 12. And I need to check if this radical can simplify. And if I think about factors of 51, I don't really know of many. Like I could start testing. I know it's not divisible by 2, but if I try 51 divided by 3, it is actually divisible by 3, which is kind of fun. But 51 divided by 3 is 17. So those are both prime. It cannot simplify further. So the cosine of p is the square root of 51 over 12. Part B. We're going to find sine of n. So sine is opposite over hypotenuse. So the sine of n, I'm looking at the opposite side from n over the hypotenuse. So the side opposite angle n, that would be OP again, over the hypotenuse, which is still NP. So the sine of the other angle seems like it's the same thing as the cosine of the first one we found, right? The sine of n seems like it's the same as the cosine of p, which is an interesting observation to kind of keep in our back pocket. OP is the square root of 51. So the square root of 51 over 12 is equal to the sine of n. And we could write that as a decimal, of course, if we wanted to, but I don't think I need to because that fraction works. Part C, I am going to find what is sine of p. So sine of p. So if I look at p, hello, there we go. Here is p. Sine is going to still be the opposite over the hypotenuse. So this is opposite side over the hypotenuse. And my side opposite, that would be ON. But I don't actually know this length, right? I don't know this opposite side. But ON over NP, that is the sine of P. So I actually need to find ON. And this is a right triangle, so I can use the Pythagorean theorem. I can use the fact that a squared plus b squared equals c squared. Or in our right triangle, the two legs, NO or ON squared plus OP squared equals NP squared. Now, I do not know what ON is. We need to find this. But I do know that OP, right, that's the square root of 51, and NP is 12. So ON squared, whatever that is, plus OP, which was the square root of 51 squared, that is equal to NP, which is 12 squared. Now, I love to see a square and a square root because those really just kind of cancel each other out. So ON squared is plus 51, square and square root cancel, is equal to 12 squared, which is 144. So to continue solving for ON, now I just need to start moving things away. To the opposite side, I'm going to subtract 51 from 144. So this tells me then that ON squared is equal to 144. Ooh, 144 minus 51 is 93. All right, we are almost done. If I need just ON, not ON squared, let's take the square root to get it to cancel. So this tells me then that ON is equal to the square root of 93, which let's see if that can break down at all. I'm going to start testing like some perfect squares. So I'm going to see, is 93 divisible by 4? Because 2 squared is 4, and it's not. Is 93 divisible by 9? Unfortunately not. Is 93 divisible by 4 squared or 16? No. So as I kind of test bigger and bigger numbers, is 93 divisible by 25? No. I actually come to find that this can't simplify any further, which is unfortunate. So I would just say that ON is the square root of 93, which means that sine of P is equal to that opposite side, ON, or the square root of 93, over NP, which NP, again, that's the hypotenuse. Our hypotenuse was 12. All right. The last small note I want to make, I'm not going to do an example. Please be careful. Remember, if you're dividing by a radical or you have a radical in the denominator, we need to rationalize it. You need to multiply by that fraction to target that radical in the denominator that you don't want. Please let me know what questions you have. I really look forward to seeing you in class and working more on this.